Hello everyone and welcome. This is Dylan presenting the end of the year project created by myself, Matthew, and Brittany for our Advanced Molecular Neuropsychopharmacology class under Dr. Rachel Penton at the University of North Carolina at Chapel Hill. This project was originally intended to be a 3D physical model created using the UNC's makerspace. However, due to the constraints placed by COVID-19, our group has decided to create this digital representation and accompanying video in order to showcase the interactions highlighted within. Our group has modeled an interaction showcased in a paper by Wang, Levit, Shoichet, Wacker, and Roth from 2018 titled Structure of the D2 Dopamine Receptor Bound to the Atypical Antipsychotic Drug Risperidone, cited below. The authors of this paper found several interactions between risperidone and the DRD2 dopaminergic receptor. One such interaction showcases that after risperidone has attached to the binding pocket of DRD2, it creates a conformational change in the transmembrane residue known as I-184. I-184 undergoes a small helical turn and then points across the binding pocket towards other transmembrane residues known as TRP100 and L94. This subsequent interaction creates a hydrophobic patch around the binding pocket of DRD2. This hydrophobic patch then dissuades other ligands from later binding to the receptor, and it is this interaction that we are going to showcase with our model. Our group has decided to take some liberties in the software to label and otherwise highlight interactions that would have been represented differently in a physical model. We will showcase these interactions when they come up. I will now go through a quick tour of the model in order to showcase what the different labels mean and also to show what everything would represent in a real DRD2 dopamine receptor. Firstly, I'd like to give some locational reference information for our model. The top part of the model represents the extracellular portion of the DRD2 receptor. The 7 alpha helices that make up the receptor span across the membrane, and the bottom of our model then represents the intracellular portion of the DRD2 receptor. These 7 alpha helices are labeled with Roman numerals 1 through 7 in order to give a more clear indication of where exactly everything should be positioned within the model. There are other important aspects of the model that have been labeled in a similar fashion in order to make it easier to represent locational information, such as the extracellular loop 1, that is a connection between the tops of alpha helix 2 and 3 within the receptor, extracellular loop 2, which is a connection on the top between the 4th and 5th alpha helices in the receptor, the L94 residue located on alpha helix 2 of the receptor, the TRP100 residue located along the extracellular loop 1 of the receptor, and the I-184 residue located on the extracellular loop 2 of the receptor. This area within the receptor, where the mouse cursor is currently located, represents the binding pocket for risperidone and other ligands within the DRD2 receptor. Now that we have all of the locational information and labels explained, I will go ahead and showcase the interaction for the model. As of right now, the binding pocket for our model is empty, with risperidone floating alongside the DRD2 dopamine receptor. We're going to simulate that this binding has now occurred. Boop! And there it is. Here we can see that risperidone has now bound into the binding pocket of the DRD2 dopamine receptor. Now we will simulate what changes occur after this binding happens. The binding of risperidone causes several conformational changes to occur within the DRD2 dopamine receptor. One such change occurs at extracellular loop 2, specifically a transmembrane residue I-184. After the binding of risperidone, I-184 undergoes a small helical turn to face across the binding pocket towards the other residues known as TRP100 and L94. This helical turn and subsequent interaction creates a small hydrophobic patch to form on the center and top of the binding pocket. This patch is represented here by small black spheres in a matrix. This hydrophobic patch acts to dissuade other ligands of DRD2 from interacting with the membrane or attaching before risperidone has unbound. And with that, we conclude our presentation of the interactions between risperidone and the DRD2 receptor, leading to the formation of a hydrophobic patch. I will now take a few moments to briefly discuss the differences that would have been apparent had this been a physical model. Firstly, in a physical model, we would have relied on paint or other ways to label and otherwise incorporate labels into the DRD2 receptor. Secondly, in a physical model, we would have included a net or mesh-like structure within the binding pocket to catch risperidone and so it could float into the correct space. Lastly, in a physical model, we would have incorporated the use of magnets in order to have I-184 undergo its small helical turn, and magnets would also have been used to physically represent the repellent nature of the hydrophobic patch after the binding of risperidone. That concludes our presentation of the interactions between the DRD2 dopaminergic receptor and the atypical antipsychotic risperidone. We will be including links in the description below to the paper from which we drew our inspiration, as well as the pages on 3d.nih.gov where we received the 3D models for the D2 dopamine receptor as well as risperidone. Thank you for your time, and we hope you have a wonderful day.